Good morning. It's my pleasure to introduce our plenary speaker today, Dr. Ann Dillner from UC Davis. The plenary today is sponsored by AEESP. Ann received her PhD in environmental engineering at the University of Illinois and had a postdoc appointment at Georgia Tech afterwards. She's currently the Associate Director of Analytical Research at the Air Quality Research Center at UC Davis. Ann brings a lot of experience from aerosol monitoring networks in the U.S., going back to her PhD projects during her thesis preparation. She's now co-PI on 3 U.S. monitoring networks and contributing to 2 international networks. Today, she'll be talking about the value and impacts of aerosol speciation networks in the U.S. And with that, please join me welcoming Ann.
Thank you, Roya, for that kind introduction. Thank you all for being here. It is wonderful and quite an honor to be able to give you the plenary today. Last year at AAAR, the Aerosol Chemistry Group, as well as the History Working Group, thought that a plenary on monitoring networks would be something of interest to our community. And I want to thank them for that, because I think that's true, and I'm excited that you're here to learn more about this. And then I want to really thank Jason Surratt for inviting me to be the person to give that talk on the monitoring networks. I also want to thank AEESP, that's the Association of Environmental Engineering and Science Professors. They sponsor this lecture, and they've been long-term supporters of AAAR, so thanks to them. So I'll be talking about 5 different monitoring networks. The first 2 are U.S. monitoring networks, and the icons for those are shown in the upper left and center of the screen, Improve and CSN. And then I'll switch gears and talk about international monitoring networks. First Spartan, and then the ground-based monitoring that the Maya satellite project is sponsoring. And then I'll end my talk talking about the new high-time resolution Ascent monitoring network. So let's start off with the oldest. We have 2 long-term PM2.5 monitoring networks in the U.S. Improve stands for the Interagency Monitoring of Protected Visual Environments. These monitoring sites are located in national parks and wilderness areas. These are called Class 1 areas in the regulations, and they're shown in blue on the map. Improve began in 1985. So this is our 40th anniversary. So congratulations to Improve for 40 successful years. CSN, it stands for the Chemical Speciation Network. The CSN is kind of an umbrella organization. It includes CSN sites, NCOR sites, and STN sites. They're all marked in red on the map. This is, as opposed to Improve, CSN is in urban and suburban environments. And it began in 2000. So let's talk a little bit more detail about the similarities and differences between these 2 monitoring networks. Both have statutory requirements. In Improve, the 1977 Clean Air Act amendments addressed the issue of visibility and said that that is something important for us to protect. And then in the 1999 amendments, the Regional Haze Rule was included, and that rule quantifies the process of how to meet regulations to improve visibility it's statewide for each state. So the objective is clearly visibility for the Improve network. But in addition, the network is interested in measuring the composition of the aerosol and the trends in those compositions. We want to use that data to understand the sources of these aerosols. And state governments use it to develop their state implementation plans, or SIPs. The SIP is required by the EPA to have the state say, this is how in the national parks or wilderness areas in our state, this is how we're going to meet the Regional Haze Rule. The EPA CSN network, on the other hand, is motivated by the 1997 promulgation of the NAAQS, or National Ambient Air Quality Standards for PM2.5. And this network is a health-based network. But just like Improve, it's also interested in composition and the trends in composition, the sources of these aerosols, and states use it to meet to address their SIPs or to develop their SIPs so that they can meet the NAAQS for PM 2.5. Improve began in 1985, as I said, with about 36 sites, with a major expansion in 2000. There are currently around 160 sites. The CSN network began in 2000 with about 13 sites, and there are currently around 130 sites. The aerosol collection is very similar between the two networks. PM 2.5 is the focus. There are 3 different types of filters that are used at both types of sites, and each of those filter types are associated with different analyses to measure different species within the aerosol. Improve is all 1 and 3 day sampling, 24 hours, midnight to midnight local time. CSN is similar, but some sites are 1 and 6 days rather than 1 and 3 days. Improve also measures PM10 because PM10 also impacts visibility. It's less important for health impacts. The speciation between the two networks are very similar. Organic and elemental carbons, inorganic ions, soil, and trace or toxic elements. CSN also includes the cations. Improve only has anions. So why is this important? What is the value of these long-term filter-based monitoring networks? I'll go through several slides looking at the importance of these networks and how they are helpful to scientists and to the general public, as well as regulators. So this map shows the annual mean sulfate concentration at each Improve and CSN site over time. So at each site, there is a time series of the annual mean sulfate concentration located at the location of their site. These time series are colored going east to west, yellow, green in the east, blue and purple in the west. And we can see right away looking at this map that in the east, the sulfate concentrations have gone down significantly. In the legend to the right, I'm showing all of these time series plotted on one graph so that you can see what the concentrations are, see the time series. And there's 2 things that we'll note from this. One is that in 2000, there was a big expansion in monitoring across the U.S. Both EPA CSN networks started and Improve expanded around that time. And again, we can see this very big decrease in sulfate concentrations. These sulfate concentration decreases were due to regulations, federal regulations, that were put into place to decrease SO2 from coal-fired power plants. And these regulations started to be implemented in the early 2000s, resulting in these decreases. These decreases are statistically significant and dramatic, and in the East, it was about 8% per year during the summer and fall. In the West, the decreases were much less. The concentration started lower and they didn't decrease as much, but about something around 1% to 4% in the West. So this aerosol monitoring network data allows us to track the success of regulations. It also allows us to visualize the change in air pollution due to regulations. Here I'm showing a picture of the Great Smoky Mountain National Park using improved data to simulate visibility in 1990 before the regulations and in 2023 well after the regulations. The simulation is using the 20 haziest days in 1990 and then the 20 haziest days in 2023. So this is the worst air pollution or the worst visibility at the site during these 2 different years. And so this data allows us to dramatically visualize the improvement in the air quality due to regulations. Improve and CSN also measure toxic elements. So in this figure, I'm showing vanadium across the U.S. Fuel oil regulations were put into place to reduce the allowable sulfur content in fuel oil. So this is a different sulfur-related regulation. And the fuel oil had to go from 1% sulfur to 0.1% sulfur when the ships were within the North American Emissions Control Area. That's designated by the bright green stars around the coast of the U.S. And the map shows data from 2011 in blue and 2015 in red. And the size of the circle is an indication of the annual mean concentration, in this case, of vanadium at those sites. And what we can see is that the concentrations before and after this regulation decrease significantly. The red circles are much smaller than the blue circles, showing again how the improved data can show a decrease in concentrations, and in this case in toxic metals, due to this fuel oil regulation. And even though improve is focused on visibility, this is a case where the improved data is used to show the impact that these regulations can have on improving our health by reducing toxic metals. I'm going to sneak one more network in here. This is the Southeastern Aerosol Research and Characterization Network, called SEARCH. They are very similar to Improve and CSN. They're filter-based. They do the same kind of analysis, same types of filters. And in this work, we use 2 urban and rural pairs. So SEARCH is located in the Southeast, and it was predominantly 2 urban and rural pairs, one in Georgia and one in Alabama. And we used filters that had been in storage and analyzed them, filters from 2009 through 2016 when the network ended. And we analyzed them by infrared spectroscopy to measure organic functional groups. So this is an effort to look at the composition of the total organic mass. And the figure on the right shows the organic mass, annual organic mass, just at one of the sites, Atlanta, over the years of the analysis. All 4 sites showed very similar data, so I'm just showing one site here as an example. So we see this dramatic or a nice decrease in OM during this time period, beginning in around 2011. So the nice thing about functional groups is that it allows us to understand more about what is in the organics. So if we look at the pink figure, the pink data on the figure to the right, that's looking at that figure is looking at the organic matter composition as a function of, as a percent. And the pink data is alcohol, so just an OH group attached to a carbon. And we can see during this time that even though there's this big decrease in OM, there's a fractional increase in alcohol. And that's consistent with monoterpene secondary organic aerosols, which there is a significant amount in the Southeast. And this was especially noticed in the spring and the fall when monoterpene emissions are strong. We also see a decrease in carboxylic acid, that's in the bright green on the figure, and this is consistent with a decrease in combustion, both a decrease in the SO2 from the coal-fired power plants, but other regulations that decreased combustion emissions, as well as a decrease in isoprene SOA. Network data, therefore, enables us to also look at changes in atmospheric chemistry. In this work, researchers used improved data from 1995 to 2014 to look at dust. The figure on the right shows the dust concentrations during this period, and it's colored by their change over the time period in the month of March. They're using iron as a tracer for soil, and this shows a statistically significant, more than 5% increase in dust in the month of March over this time. They also showed a strong correlation between the dust concentrations and large-scale climate variability. So the Pacific decadal oscillation during 2007 to 2014 was in its negative mode, which led to drier, windier, and less vegetated conditions, making for conditions where dust was more likely to be aerosolized. And this paper is the first time that the association between the PDO and aerosol concentrations, specifically soil, was reported. This work shows that we can, again, use decadal or use network data to quantify the changes in air quality, and then further goes on to talk about what these changes, what the implications are of these changes. And they include a change in the hydrological cycle. So when the dust lands on the snow, that changes when it melts or how fast it melts. So that changes the hydrological cycle. There's a decrease in visibility. So in the east, I showed this really nice simulation of the improved visibility due to SO2 regulations. But in the west, the increased soil is actually decreasing visibility currently. And then finally, dust carries a fungus that leads to, that when inhaled, leads to valley fever, which is a very terrible respiratory disease. And we've seen an increase in the last decades of valley fever due to increased soil. And valley fever's been in the news again lately due to its increase in our country due to more soil in the atmosphere. So another work, so that work looked at measured concentrations and how it affected or how it affected different aspects of our life. This work uses improved data as a starting point, and then uses climate models to project into the future the impact of soil on health and mortality. So improved data from 1988 to 2005 was from 35 sites in the Southwest was used, and that's the blue bars that you see on the graph. They're showing the hospital admissions and the all-cause mortality for 20-year bins. So the first bin is 2010 to 2020 to 2040, and goes on up. And the increase in these health effects are due to things like aging population, more people being in the Southwest. But the air quality in this model, it has not changed. The soil has not changed. Then they used two different climate scenarios to look at the impact of how much the soil would increase, and then how does that affect the hospitalizations and the mortality. And you can see in both of the climate scenarios, there's a significant increase in negative health impacts due to the increase in soil based on their climate simulations. So network data in this case allows us to have a baseline for health impacts and then look at the effects of climate change. Improve and CSN data both can be used and are used importantly to evaluate health impacts. This figure uses both Improve and CSN data to look at organic carbon. So the data goes from 1989 to the present and is split up into 3 bins. The top figure is the 90th percentile of organic carbon in these networks. The middle is the median value of organic carbon, and the bottom graph is the 10th percentile over this time series. Each data point is colored by month, with the lighter months being, or the earlier months, January, February, being the lighter colors, and the later months, November and December, being in the darkest blue colors. And what this figure shows is that organic carbon was consistent for about the first 2.5 decades of Improve. It did not vary by a lot. But in the last decade, we've seen large increases in organic carbon, especially in the summer and fall, due to increased wildfire activity brought on by a warmer climate. So we're using improved data and CSN data here to show the impact of climate change. In a very recent paper out of Nature that was picked up by the New York Times, they looked at the impact of mortality on, or the effect of increased mortality due to this increased wildfire smoke. So in this case, Improve and CSN data were used with geochem modeling and satellite AOD data to estimate monthly PM2.5 concentrations, and then a model was used to estimate the smoke fraction of that PM2.5 concentration. This figure from the New York Times shows that in current observed data, the concentrations of smoke are mostly in the west and relatively low, but by the middle of this century, that smoke will have spread way into the Midwest, and the concentrations will be considerably higher. They then used this model to estimate the impact on human health, particularly on mortality, and showed that this increase in smoke will kill an average of 70,000 Americans per year by 2050. So the network data again allows us to identify impacts of climate change and then the resulting effects on human health. Now I want to switch gears. That was improving CSN, all U.S. focused, all these long-term, quite old, wonderful speciation networks. And now I want to talk about how that's been expanded into international monitoring. So the Intergovernmental Panel on Climate Change, in its most recent report, showed this figure, and it shows the composition, the same things I've been talking about, OCEC, sulfate nitrate, around the world using permanent monitoring stations. If we zoom into the map, we can see the black markers are the observation locations for the data that the IPCC used to estimate these aerosol concentrations. And in a place like Africa, we see 3 or 4 dots. And in Asia, still not very many, 1 or 2 in Australia, a handful in South America. Whereas there are a lot, I'm not saying too many or enough, but a lot in the U.S. 2/3 of all these monitoring sites are in the U.S. In addition, these places where there is lacking monitoring often are places where the concentrations are very high, such as in Africa or South America. So the Spartan network was developed to try and remediate this problem of having not enough monitoring data in these international locations. Spartan stands for Surface Particulate Matter Network. It began in 2012. The sites are located in low and middle income countries. These are located in cities with high urban density and with very low or little monitoring data, and in cities that have high pollution. That was an important part of their selection criteria. So the objective of the Spartan network is to evaluate and enhance satellite estimates of PM2.5 and the resulting health impacts. Spartan, unlike improving CSN, just uses one filter type, but they are able to measure do all the different analyses or all the different concentrations of species just using the Teflon filter. They collect PM2.5 in 1 and 3 day cycles, similar to Improve, 9 a.m. to 9 a.m. For some of the sites, and other sites, it's still a 24-hour sample, but it's collected over 9 days, so a few hours each day of those 9 days. The species, again, are organic and elemental carbon, anions and cations, and soil and trace elements. In addition, the Spartan network has the goal to be co-located with nephelometers, as well as Aeronet sun photometers to get aerosol optical depth, as well as other measurements from the sun photometers to help with this connection with the satellite data. I don't believe I've mentioned yet, and it's just occurring to me, that all this data that I'm talking about is publicly available. And I've been putting the URL at the bottom, so if you want to look that up later, you can. All of these networks, one of the things that they offer is publicly available data that we can all use in our research, we can use it in teaching, and the public can use when they're concerned about the air quality, either where they're going or where they live. And that is an important aspect to this, that this is free and available to everybody, that government officials, anyone who wants to use this data. So a recent Spartan project looked at black carbon, and they looked at black carbon emissions in the global north versus the global south. They used Geochem in the high-resolution model, the GCHP model, which has a resolution of about 25 kilometers, and they used 3 widely used BC inventories, although I'm just going to report one here. They showed good model to measurement agreement in the global north. That's the points shown in the blue. The x-axis is HIPS data from the Spartan network. HIPS is an absorption measurement on the Teflon filter that Spartan collects. And they compared that to their simulated black carbon measurements or black carbon estimates from Geoschem. And again, in the blue, we see this very good correlation between the measured and the model data. However, there's poor correlation in the global south. That's the points that are marked in red. And especially sites like Dhaka and Addis Ababa show really complete disassociation between the measurements and the model data based on the available emissions inventory. And so these researchers came to the conclusion that these were based due to inadequate emission inventory. The network data points in this case are used, are telling us that we need to have these consistent long-term measurements of black carbon so that we can do better at modeling them, so that we can better understand how black carbon affects health worldwide as well as climate.
Good.
The NASA Mission to Earth Multi-Angle Imager for Aerosols, or MAIA satellite, also sponsors ground-based filter monitoring. This satellite is intended to measure aerosol composition in a set of globally distributed target areas. Those target areas are shown on the left map in bright blue and green rectangles. And the way the satellite will work is it will pass over these sites as frequently as possible and step and stare across that site. So it will look at that site all the time that it is moving across the sky above it to get very high density data for these in these target areas. MAIA is currently expected to launch no sooner than 2026, next year, but the surface monitoring data sites have been operational. And so, and that's the focus of what I want to talk about, are these surface monitoring sites. The objective of the MAIA satellite is to understand health impacts of aerosol in these globally distributed target areas, these blue and green locations. So the data that the satellite will use, that they will use to connect measurement or aerosol species on the ground and the satellite signals themselves, come from many places. One of them is international data sources. Things like OpenAQ agglomerates data, and they are using that data any place that they can get data internationally they're pulling from. But they're also using Spartan Network data, and in fact have expanded the Spartan Network site, have supported additional sites in Spartan. They support monitoring that is being done out of Colorado State University. Those certainly are using Improve and CSN data. And F-Labs has some microAEES at some of these sites as well. So in this work, we used one Spartan MAIA site at Addis Ababa, Ethiopia, to look at sources of organic carbon. And we used, again, FTIR to do that. Ethiopia is a low middle income country in Africa and sub-Saharan Africa. We used the first full year of Spartan samples, which was 2023. And the figure on the right shows the time series of that data. The seasons for in Ethiopia are not sort of identified the way we identify them. Their identification is through rain. So in the winter, it's very dry, almost no rain, and so that's the dry season. And because we used January to December, we have 2 dry seasons in that year. And then March, April is a less rainy season. And then May through roughly September is a very rainy season. So we use the spectra from the FTIR to put into positive matrix factorization, or PMF, to identify sources from these spectra. And what we can see from the figure is that the coal and wood burning, which comes from home heating and cooking and is shown in green on the figure, is between 50 and 90% of the organic aerosol during the rainy season, and even during the dry season, it's between 20 and 80%. Fossil fuel combustion is also an important source. They burn mostly diesel in their cars and in generators, and during the dry season, that's up to 80% of the OA is due to combustion. So networks provide the extent of data that is needed to do source apportionment. We can't do source apportionment on just a small amount of data. So networks give us this long-term data that allow us to do source apportionments of all kinds. Now, the last network that I'm going to be talking about is the high time resolution network called ASCENT. As Jason mentioned, there is during lunch today, if you'd like to learn more about ASCENT, please come join us with your box lunch. ASCENT stands for Atmospheric Science and Chemistry Measurement Network. It is funded by the National Science Foundation. It is a high time, real time, all the time network. So the instruments here are high time resolution. These are not filter-based networks. This is not a filter-based network. The infrastructure grant from NSF was funded in October of 2021. We had all sites up and running by May of 2024. And just last month, we learned that operations funding will be continued for the next 5 years for ASCENT. The map on the right shows the 12 ASCENT sites. You'll notice that they are located with Improve or CSN or other network sites. There's a site in Southern California that is located at a South Coast Air Quality Management District site. The site in Alaska is located at an NSF ecological network, the NEON network. And in Houston, we're located at a site that is part of a local Houston network of aerosol measurements. So this is a good time to talk about the cooperation between networks. It not only takes a lot of people to run a network, but there's also this nice cooperation between these groups of folks to support each other's work. And in this case, for these longer term networks are providing support, infrastructure support for the newer ASCENT network. ASCENT each site has 4 pieces of monitoring equipment. The central one being the Aerosol Chemical Speciation Monitor, or the ACSM. We're using a PM 2.5 inlet on a TOF ACSM. ACSMs were developed by Aerodyne to be able to run unattended for long periods of time for the purpose of doing aerosol monitoring. ACSMs, like AMSs, measure organics, sulfate, nitrate, ammonium, and chloride. The next instrument is an EXACT. This is by Cooper Environmental, also PM 2.5. It measures trace elements, and we're also using it to estimate soil or lighter elements. An aethalometer from McGee Scientific, the AE33, also PM 2.5, to measure the black and brown carbon that ACSM is not able to measure. And then we also are getting particle number, size distribution, and number of concentrations from a TSI SMPS. This data is not currently publicly available, but our plan is to have it publicly available by spring next year. We'll provide both the immediate real-time data that's not QC'd, as well as batches of QC data over the beginning part of our time as a network in the spring of 2026. So I want to highlight 2 cases where, although we've just been in the infrastructure part of this grant, we still use this data and to identify and help in important situations. The first being the Los Angeles urban wildfires that occurred just this January. ASCENT was highlighted in a January 20th New York Times article. The caption on the figure says, "Researchers use a new network of sensors to track chemicals in the Los Angeles air basin in real time." And one of our ASCENT graduate students almost immediately published a paper in a CDC report called the Morbidity and Mortality Weekly Report. And she used this, the top figure on the right, showing hourly data from the EXACT instrument of lead, PM 2.5, at the Pico Rivera site. And what we can see is on January 7th, the Palisades fire and then the Altadena fire started. The plume reached the Pico Rivera site in late morning of January 8th, and then peaked in the morning of January 9th, and continued to be visible at the site until around the middle of the January 11th. The highest concentration was around 0.5 microgram per meter cubed. That seems really high, certainly higher than anything ASCENT had seen before. But we were able to use CSN data. There's a site in LA, not co-located with Ascent, but this is the CSN North Main site in LA that gives 24-hour lead concentrations. And you can see that the scale is the same, a 0.5 microgram per meter cubed of lead. And this is looking at data going all the way back from 2018 to current. And you can see, yes, indeed, this concentration of lead in the LA basin during these wildfires was unlike anything that LA had seen in the last 7 or 8 years and beyond. So in this case, again, we're able to have context of the new high time resolution data from the CSN data. Another situation where we looked at network ascent data, this time we're using aethylometer data, and we have 4 sites in the southeastern U.S. this time, Pittsburgh, well, not south, the eastern U.S., Pittsburgh, New York City, Atlanta, and the Great Smoky Mountains National Park site. And in this case, there was a prescribed fire. So in the southeastern U.S., every year, when the weather is right, when the weather is prescribed to be the best it can be for smoke distribution, the people are allowed, the government is allowed to start fires to get rid of underbrush and other things that need to be handled so to minimize the possibility of wildfires. So when that happens, all of the Southeast lights up with fire. And what we can see in our aethylometer data at each of these sites, starting in March 7th, very little black carbon, very little black carbon. And then all of a sudden on March 13th, we see this big spike in elemental carbon. And we can see that the day of the event. We can see it as it's happening. The AirNow Tech map that I'm showing on the right shows all the prescribed fires, but that wasn't available until the day after the event. So although that's very fast, Ascent, when we get the data up and running, people will be able to look at it in real time. So I have 2 concluding slides. The first is about challenges. Aerosol speciation monitoring networks are not without their challenges. First is instrumentation and technology changes make consistent measurements challenging over decadal time periods. If we think about 1985, when Improve started, the technology was completely different than we have today. And we can't keep doing exactly the same thing for 40 years because the technology changes, and we don't want to. We want to continue to do the best we can technology-wise, but we also want to have a data stream that's consistent so that we can measure trends. So to address this issue of changes in data, Improve and CSN publish what are called data advisories, and those are online and can be accessed at any time, as well as if you download the data, there's metadata that gives you information about changes in instrumentation or other things that could change the concentrations that you're seeing. In addition, there are many publications about this in the literature. I've just listed a few here to talk about the XRF instrument changed here, and so these particular elements you cannot look at trend-wise across this time period because the instruments just measure this particular toxic element too differently, or here's things that did work fine across that transition. You can measure these things or look at trends across these transitions. Large spatial and temporal scale coverage requires considerable funding and infrastructure such as space and power and internet. And we know right now funding is a challenge, but this isn't the first time. It maybe is the worst time, but it's not the first time that funding has been a challenge. So that's another difficulty. Filter samples, which most of the networks I talked about have low time resolution, 24 hours, and a delay. So if a filter is collected in Addis Ababa, Ethiopia, it has to be shipped back to Washington University and then on to my lab and then back to WashU, and then QC has to happen before it gets put online. So there's this delay of many months. Improve tries to get their data out within a year. CSN, it's closer to 6 months, but there is this delay. High time resolution instruments and satellites require additional higher levels of funding and higher levels of expertise to operate, but provide this additional time resolution and specificity. So there are strengths and challenges. So aerosol speciation monitoring networks, what is at stake? These networks provide crucial data to understand the impact of emission reduction regulations, to understand changes in air quality and atmospheric chemistry, to understand the sources of air pollution so that we can then make prudent decisions about how to control these sources to decrease air pollution. They allow us to understand the impact of air quality on climate change and vice versa. And they allow us to establish the link between air quality and health impacts and mortality. Without these networks, these types of efforts, these important worldwide efforts, will be degraded or lost. I want to end by thanking all the folks who help make these networks run. The figure in the upper left is my team at UC Davis, the Air Quality Research Center. We run both the Improve and CSN networks. The Spartan team, Randall Martin's group out of Washington University. This is a science meeting, a picture of a science meeting that they had recently. The Maya team is shown in the lower left. This is a science meeting. The Maya team is amazing. It goes all the way from satellite engineers to epidemiologists and all the air pollution and data people in between. And then our new Ascent team, many of whom are here today. And with that, I'd like to say thank you for your time. I appreciate your attention, and I'm happy to take questions.
We have time for questions.
Yes, please come to the mic. Thanks.
Hi, and great talk. C.Y. Wu from University of Miami. I think the network has wonderful data for the physical and chemical characterization space. I'm just curious, what's your thought about the biological component? Please. Thank you.
We have filters in near my building stored for decades that if someone wants to use them to do some kind of analysis to learn more about the biological impacts, they can reach out to me and I can reach out to the steering committee to use those to do analyses that tell us more about the biological impacts. People are already doing that. That is happening to a lesser extent. It's not currently a part of our routine analysis. That would be great at some point. Thanks, CY.
Excuse me. Thanks for the great talk. Joel Corbin from NRC Canada. Could you talk a bit more about how we can, the synergy between satellite monitoring and ground-based monitoring? Because obviously we have a lot more detail from ground-based, but do we need to plan the monitoring sites so that we can interpolate appropriately with satellites, or what are your thoughts on that?
That's a great question. That is the intention of Maya, to understand how those two are related, to understand how the satellite retrievals give us PM 2.5 speciation data. And the hope is that by training that data in these particular sites, that will help us understand the satellite retrievals at other sites. But definitely additional ground-based monitoring would firm up that relationship at different places. And so including more monitoring. So right now, like Ethiopia has one site. There are many countries in Africa that have no sites, no monitoring. But by adding monitoring at these different sites that have different cultural, different behaviors, different emissions, would really help connect those two together, the satellite and the ground-based data. Thanks for asking that question.
Hi, Ann. Chris Kappa from UC Davis. Following up on Joel's comment, to add a site at each country, say in Africa, what would be the marginal cost to add one site? I imagine it varies around the world because it depends on labor, but in a sense, what would be the marginal cost on your end?
Yeah, I don't actually know that. I think an approved site is something like $50,000 a year. but that's a U.S. site, so we would need to include additional transportation. There are certainly challenges. There are language barriers sometimes. There are tariffs. There are when the filters come back to the border patrol is like, what is this? Is it dangerous? You're measuring toxic things off this. What's going on? So there's certainly issues with that. The Spartan Network really tries to keep the prices low, and they do as much analyses that is non-destructive and as inexpensive as possible to enable a larger range of sampling at different locations. I hope we can do that. I hope we can add more sites. But satellites are also so important because we're never going to be able to do, I mean, if you think about it, in California, we have a site, say, in Fresno and in Lake Tahoe or somewhere, and they're close. They're, like on that map that I showed, they're practically on top of each other, but their concentrations and the emissions and the speciation is completely different. So, and we're talking about just one site and one sample in an entire country. So it's really important to get more monitoring data. Yeah.
Yeah, thanks, and great talk.
Thank you.
And have you ever done the job to retrieve aerosol-related data like optical depth from radiation measurement network to use your data against the satellite data and retrieve data and for big, extended simulation work?
Do you want to tell us a little bit about your network that has that data?
Sure.
I know that's a leading question.
Yeah, I'm professor at Colorado State University, and I'm running USDA ultraviolet radiation monitoring network. We have 41 stations, and we have 40 years data. We actually retrieve aerosol-related data from our network. I just wondering, we had a talk day ago, and that's what I want to ask: is there any potential and to develop a model to retrieve for national, international data, to work together against the satellite data as well?
Yeah, that sounds great. To answer your initial question, I have not done that, but I think that there's a lot of room for collaboration, and I'm really excited about the idea.
Okay, thank you, Anne.
Thank you.
Hi, I'm Alexandra at UNC Chapel Hill. I was curious as to whether, due to the challenges of getting real-time aerosol speciation, and then also the challenges of getting filters from the Global South to analysis in the US, are there any initiatives to set up infrastructure in the Global South for doing analysis locally?
That is a fantastic question. The extent that I know about that is my graduate student who recently finished with me is from Pakistan. He's back now in Pakistan as a professor. And so I'm working with him one-on-one individually to do that, to get infrastructure in his university so that he can better understand the air pollution in Pakistan. I don't know of any broad-based or government-based initiatives to do that, but it seems critically important. We shouldn't be sort of imposing our ways and everything that we have learned a lot, and we can train other folks, and then they should do what's best for their country and their particular sources and information. So I hope that will come about. Thanks for a great question.
Great, thank you so much.
Thanks for the great talk. So I'm Yiming from University of Miami. I'm a student. So I have a question is that, with nowadays, with the communication services, like Starlink, more like lower cost, more available. So is that also it will also help to promote to have more easier deployment of those aerosol monitoring system, maybe for those areas which are having those satellite communication services?
Thanks for that question, and I don't know the answer. if anyone would like to address that, I'm happy to hear, but that's a good question. I don't know.
So Dan Murphy, first, I'm always impressed by the wisdom of the people who set up the improved network to measure more than just visibility. My question is, we tend to focus on aerosols on the sources and emissions, but the concentrations are also set by removal processes. And I wonder if you have some good examples of where the network data has been used to, train model removal processes, dry and wet deposition.
That's also not in my field of expertise. I don't know cases of that I can recite off the top of my head. But I do know that people are very interested in the deposition process, and there have been some talks here at this meeting trying to understand these removal processes, and they are important, certainly.
Hi, Ann.
Hi.
Mitchell from Yale. Thank you so much for the lovely talk. I was wondering, it seems that nowadays there's a fair amount of inertia in where we put monitors, as in, there's already filter monitors here. There's some trace gas monitors here. Let's throw the Ascent network here. Let's throw, and then we have almost like super sites with lots of monitors. But I was wondering, and there's still some new Improve and CSN sites popping up in Spartan sites. I was wondering specifically in cities, how does the discussion on the back end look like for placement of sites? And, it has large implications for environmental justice initiatives and community science. And so there's a lot of work that goes behind it.
Yeah, that's a great question, Mitchell. Thank you. In the Improved network, siting has to do with things like, can you access the site? The trees have to be far enough away from the site so that it doesn't impact the concentrations. In urban sites, there are other factors like you don't want to be too close to a major source. You're trying to get the general, when you have just one or two, like one CSN monitor in a city, you don't want to get just one factory or one big highway. You want to try to get the over sort of the general air pollution in that city. But there are also things like is it government land? Is there access? Is there power? There's all these different things that are not necessarily scientific that go into these decisions. So I think that's a place where things like sensors, low-cost sensors come into play so that we can get a broader range of concentration measurements around a city. I also think that for EJ purposes, we should be looking at places in cities where that's an important thing to be, that are not currently being monitored. I don't know how to make that happen. Yeah, thanks.
Hey, this is Suresh Daniela, Clarkson University. You just touched upon low-cost sensors. And, during wildfire recently, we got contacted by a lot of news agencies, for example, because in very rural areas, we were seeing concentrations that we've never seen before, up 200 microgram per meter cube. And so there's a lot of reliance on data coming out of low-cost sensors. That was the only one sometimes near us. So where do you see this fitting in these networks? And if you talk to people in Global South, there is actually quite a bit of a movement towards increasing this network. So, where do you think this is?
Yeah, I think low-cost sensors are absolutely important. They are going to be able to give us this spread around cities. My town, Davis, California, there are 200, I don't know, maybe more sensors in my town. So I can see the plume come across the town. My husband's family in upstate New York, there's not a single purple air monitor there. So they just moved, and my husband gave them as a housewarming gift a purple air monitor. But the Ascent network, so one of the things about monitoring, about sensors, is that they are not as reliable, and they're only measuring mass generally. But the Ascent network and the Improved network, and actually I think also the CSN network, has some co-location. So the Ascent, all the Ascent sites have at least one sensor in addition to our more expensive instrumentation. And we need to be using, and I know South Coast has also done a bunch of work on this to try to evaluate the quality of that data. And that's something that needs to continue. And things like, how do we know when it's starting to fail? When this particular sensor is starting to fail and getting that fixed or a new one put in. Those are important things. But I think sensors are complementary to what the networks are doing, and both are needed. Thanks, Suresh.
Thank you very much, Anne. I think in the interest of time, we should move on, but let's thank Anne again.